over a century, the behavioral sciences have been anchored to a singular assumption: the existence of the G factor. This is the concept of general intelligence, a unified, genetically fixed trait that allegedly dictates cognitive ability across all domains of learning. This paradigm rests on a specific premise. It assumes that intelligence is a pristine, isolated property that operates in a decontextualized vacuum, independent of the environment around it. To measure this supposed vacuum state, we built an entire architecture of standardized testing. The traditional examination room is designed specifically to strip away context, forcing the brain to solve abstract problems in artificial isolation. To test where this model breaks, we have to pull intelligence out of the testing room and place it into an extreme environment. Take the Yupik population of southwestern Alaska. These communities live across vast stretches of frozen tundra. Navigating this terrain requires highly specific, complex geographic and spatial competencies to identify landmarks in an otherwise featureless landscape. The children here develop expert-level environmental adaptation and spatial reasoning. Yet when given traditional school assessments, these same children routinely fail. Teachers brought in from the outside often view these students as hopeless academically. Meanwhile, those students possess the objective survival mastery required to keep themselves alive in an unforgiving climate. This disconnect reveals a critical flaw. Intelligence appears to be far more contextual than a global factor, as high-level survival competence fails to map onto conventional academic metrics. This anomaly extends far beyond extreme environments. Conventional ability tests consistently fail to predict actual adult life success across the general population. This chart visualizes the limits of standard metrics. Traditional intelligence and standardized tests predict only about 10% of the individual difference variation in occupational and real-world outcomes. That leaves 90% of human behavioral variance entirely unexplained by the metric we use to define intelligence. To account for this discrepancy, psychologist Robert J. Sternberg proposed a different framework. Sternberg's premise is that intelligence is not a static precursor to competence. Instead, it is a dynamic set of developing competencies. These competencies do not manifest uniformly. They organize and structure themselves in direct response to immediate environmental demands. Treating intelligence as a fixed precursor overlooks how human capability is actually engineered by its surroundings. Sternberg's 5-element structural model of competence includes motivation, metacognitive skills, learning, thinking, and knowledge. Metacognitive skills act as the executive function for controlling cognition and allocating mental resources. These resources apply to thinking, which divides into analytical, creative, practical, and wisdom-based skills. These thinking skills generate knowledge, declarative knowledge of facts, and procedural knowledge of how to execute a strategy. This knowledge forms a feedback loop, continuously refining the individual's metacognitive skills based on accumulated experience. Sitting at the center of this model is motivation, which encompasses both the drive to approach success and the urge to avoid failure. Motivation acts as the indispensable engine of the framework. Without the drive to engage, all other cognitive elements remain inert. Individuals cycle through this feedback loop repeatedly. Through deliberate practice, they generate the skills necessary to achieve successively higher levels of expertise. When we look at conventional intelligence tests through this lens, their limitations become obvious. They measure a frozen snapshot of the knowledge node, while ignoring the dynamic engine that drives competence in the first place. To test how this model adapts to different environments, researchers conducted a study with children in rural Kenya, measuring informal, environmentally adapted knowledge. The specific metric they looked at was tacit knowledge regarding the identification and dosing of natural herbal medicines. For these children, this informal knowledge is a routine, critical tool for physical adaptation and survival, yet it is never assessed on any test given in their schools. The study compared their scores on an indigenous knowledge test against their scores on an English language vocabulary test used in the classroom. The results revealed a highly counterintuitive statistical reality. This scatter plot displays the relationship between the two skill sets. The correlation was significantly negative. The higher a child scored on Indigenous knowledge, the lower they scored on the school's vocabulary test. Ethnographic observation provides the explanation. Families in the village must allocate their cognitive resources based on their immediate values. They either prioritize village survival competence or they prioritize Western schooling competence. They rarely have the resources to maximize both. The Kenya data suggests that cognitive abilities are often developing forms of competence, structured by environmental values, rather than a singular innate factor. To test how alternative assessments function in Western institutions, researchers launched the Rainbow Project, an empirical attempt to supplement standard college admission metrics. The baseline constraints for admissions have long been the SAT and high school GPAs, which exclusively measure analytical and memory skills. The Rainbow Project augmented the standard SAT by assessing creative competencies. They used exercises like counterfactual analogies, requiring students to solve abstract problems based on false premises, such as money falls off trees. They also tested for practical competencies, using situational judgment inventories, requiring students to navigate everyday scenarios, like resolving workplace conflicts or managing a difficult roommate. This bar chart outlines the major statistical outcome. It shows the baseline predictive variance of the SAT alone for predicting first-year GPAs. When the rainbow measures of creative and practical skills were added, the predictive variance roughly doubled. The researchers also set out to address the demographic disparities inherent in conventional testing. By incorporating a broader set of skills, the rainbow assessment substantially attenuated the performance differences between ethnic groups. Historically disadvantaged groups, particularly Latino and Black students, showed the most significant reduction in variance from the mean. A broader assessment of competencies yields a much more accurate predictive model that is also inherently more equitable. Experimental testing is one step, but operationalizing it at scale is another. This transition occurred with the Kaleidoscope project at Tufts University. Rather than administering a separate exam, Tufts integrated these multidimensional assessments directly into their Common Application Supplement. Admissions officers evaluated applicants along 4 tracks: analytical, creative, practical, and a track for wisdom-based skills. In this context, wisdom was measured specifically as the ability to balance personal, interpersonal, and institutional interests toward a common good. There was an obvious institutional fear. If a university abandons the strict G-factor model, would it lower the overall academic quality of the admitted class? This graph tracks the operational results. In the first year, the average SAT scores and high school GPAs of the admitted class actually rose. Simultaneously, demographic diversity expanded, with a 30% increase in African American admissions and a 15% increase in Hispanic admissions. Granting students the chance to showcase their specific cognitive strengths resulted in a stronger, more diverse applicant pool. The empirical data demonstrates that broadening our definition of competence enhances institutional excellence rather than diluting it. The old methodology operated on selection by deficit. It functioned by rigidly defining a single scale and then searching for exactly what a student lacked. The new methodology operates on selection by strength. It maps out multiple contexts to find exactly where a student excels. These outcomes suggest that G is an incomplete metric, and that institutional selection should account for how environment shapes capability. Competence is a dynamic, highly contextual, and multidimensional system, driven directly by motivation. Continuing to rely on standard models that predict only 10% of adult variance overlooks massive amounts of human potential. Instead, we have to assess the full spectrum of cognition: the analytical, the creative, the practical, and the wisdom-based. To engineer a more competent society, we have to stop measuring intelligence by how it exists in a vacuum. We must measure it by how it transforms the real world.
Please do subscribe.